So, we were talking about the theta projection concept method that was developed by Wilshire and co-workers as a way of modeling the creep behavior of materials. So, Wilshire and co-workers, so they said that instead of relying on transitions in creep mechanisms, which may not be completely correct, they said a single dislocation based mechanism with some parameters which accurately capture the creep curve, together they can be used to predict the creep life of materials. And in fact, the theta projection concept is even able to account for the transitions which are coming from conventional creep analysis methods of explaining transitions as change in deformation mechanisms. So, moving away from the theta projection method, now we are going to talk about an approach which involves modeling of creep life using continuum damage mechanics. So, in the continuum damage mechanics, essentially as you know, in a creep curve you move from primary to secondary, from secondary to tertiary, and in the tertiary region we are saying there is this generation of defects within the material, voids and cracks which start growing as a function of time, and when they start growing the creep rate of deformation is accelerated. Now, this aspect is used in continuum damage mechanics. So, what they are saying is this material damage that happens within the material, the damage that happens within the material is irreversible and is caused by mechanical loading and other environmental features experienced by the material during creep, and this damage eventually leads to very high strain rates of deformation and failure, which is what we associate happening in the material during tertiary creep. Now, the damage that they talk of is the damage that we already know in tertiary, which is like cavity formation or voids, cracks, etc. So, similar thing, similar concept. So, the damage that they say is the same thing that I mentioned. So, it is either cavity formation within the material or generation of micro cracks at some stress concentrations, or it could be just gross plastic deformation like slip happening over certain preferred slip planes, or it could be strain or aging induced coarsening of precipitates or dissolution of precipitates, etc., which can render the material weak. Other mechanisms of damage. So, these are result of creep deformation, but in addition to that you could have other mechanisms of damage happening within the material, such as you could have the material undergoing fatigue while also experiencing creep, or there could be some amount of surface oxidation which leads to loss of material from the surface, or loss of material that can bear strength from the surface, and you could also have internal corrosion if the environment is corrosive in nature. So, all these other mechanisms of damage are also introducing defects and damage into the material. Now, some of these mechanisms such as fatigue may not be temperature dependent, but their interactions with creep, such as creep fatigue interaction, can also have significant effects on high temperature damage accumulation. So, the continuum damage mechanics approach takes into account all the damage that is happening because of the different mechanisms operating while the material or component is in service. So, the different damage processes are such as ductile creep rupture, or you can have intergranular cavitation during creep, or you could have continuum creep rupture, continuum fatigue damage, environmental damage, and like I mentioned earlier also you could have aging and strain induced hardening and softening within the material. Now, in continuum damage approach, the continuum damage mechanics approach, you basically take a holistic view of the damage process and you take into account all these different damages that are happening within the material and then model creep accordingly. Now, in that sense it is more powerful than modeling creep life based on strain rates of deformation associated with a certain creep mechanism, because that is only looking at deformation rates within the steady state where defect generation has not happened yet, and also it is only looking at the role of creep and the importance of creep on the or the influence of creep on the service life of the material. In contrast to that, in continuum damage mechanics you are basically looking at damage as a process or damage occurring due to all these different processes such as fatigue, creep, oxidation, etc., acting together. So, in that sense CDM or continuum damage mechanics is going to provide you greater accuracy in creep life estimation. So, that is the advantage of CDM. Now, a well known CDM model. So, there are several models that have been proposed for continuum damage mechanics, but one of the popular CDM model is the one proposed by Khashanov and subsequently refined by Rabotnov. So, you can call it as the Khashanov-Rabotnov model. So, Khashanov basically described continuum damage as an effective loss in material cross section due to the formation and growth of internal voids. So, when you have formation and growth of internal voids, there is loss of material connection, and as a result certain sections of the material are going to bear higher are going to sustain higher loads, or they are going to share more of the load compared to the regions which are devoid of the material. So, naturally the sections which are taking up the load are going to be under higher stress. So, he introduced the concept of an internal stress. He said the internal stress corresponds to a nominally external applied load increases with increasing damage. So, the point is, as damage increases, you are the material cross section is coming down, and because the material cross section is coming down, for the same load applied, initial applied load, now the material is under higher stress. So, there is a increase in the stress with increasing damage. And so, Khashanov assumed, and Khashanov said that the damage that the material is experiencing could be described by a quantity which he called the continuity, and the continuity is basically the ratio of the remaining effective area to the original area. Like I said, because of the generation of defects or the change in cross section of the material, you are essentially the effective area of the material is coming down. The effective area is the area which is bearing the load. So, that is coming down, and it is coming down with respect to the original starting cross sectional area of the material. And so, he said the continuity is essentially the ratio of the effective remaining effective area to the original area, and this is how the internal stress will depend on these two terms. One is the initial applied stress and the second term is the continuity. Now, the continuity term was originally proposed by Khashanov, but later modified by Rabotnov, and he called it the damage parameter, where damage parameter omega, where omega is equal to 1 minus A over A naught. And by assuming a power law dependence of stress, the creep strain rate was described by the following equation. So, first Rabotnov modified this, and then he introduced this parameter called omega, and then he said a power law dependence of the stress, the creep strain rate can be described by the following relations. As he said, there is a relationship between the creep rate and the stress through a power law, and these are the terms that were introduced, where m and p are the material parameters, and as we can see here, the creep rate is inversely dependent on omega, which means if omega is increasing, then 1 minus omega is coming down, which means if the denominator is coming down, then epsilon dot c is going to grow or become higher. So, the creep rate becomes higher as omega becomes higher, and as we said, omega is the damage parameter. So, as omega becomes higher, you have more and more creep rate. So, in the case of Khashanov's approach, Khashanov assumed that damage is basically a function of the initial stress, but Rabotnov believed that this should rather be generalized by saying that the damage is not just dependent on the initial stress, but it is dependent, is instead a function of the instantaneous stress. And so, he described the rate of change of damage. So, Rabotnov described the rate of change of damage as a function of he basically gave the following equation. So, he said the rate of change of damage is a function of omega, sigma naught and things like that. And if you integrate this equation after taking into account epsilon dots c's dependence on k sigma naught m, what we eventually get is an expression for the creep strain. So, epsilon c is the instantaneous creep strain, and it depends upon the following terms, where epsilon c is the instantaneous creep strain, epsilon r is the rupture strain, T is the time and Tr is the time to rupture, and lambda is known as the damage tolerance factor. So, this is the equation for creep strain that can eventually be arrived at after looking at all the equations. So, if you look at this equation and then take it in along with this, then one can eventually arrive at the following equation. Using this equation, using this particular equation, you can develop a creep curve. So, basically strain versus time curve using the previous equation. So, in this creep curve there are a few terms that need to be introduced. First you have Tr. So, Tr, like we said, is the time to rupture, and epsilon r is the strain to rupture corresponding to Tr. If we use the steady state creep rate like is generally used, so then the steady state creep rate would actually predict a strain of epsilon dot s into Tr. So, up to Tr the creep strain coming from the steady state process. So, Tr is the point where the material has failed, and at the point of failure we know in the tertiary creep regime you have a lot of these defects generated and all that. So, that is lot of strain getting concentrated at localized regions. So, you cannot necessarily call it as uniform strain. So, the contribution of uniform strain which is coming from steady state creep rate can be determined by the following equation. So, the amount of uniform strain up to Tr will be given by epsilon dot Tr. So, this term, the uniform creep ductility is equal to epsilon dot into Tr, and as we can see from here epsilon star and epsilon r, which is the strain to rupture, epsilon r is greater than epsilon star. So, and one way of describing it is epsilon r is equal to lambda times epsilon star. So, now if we go by this view point, then when lambda is equal to 1, so if you have lambda is equal to 1, then basically epsilon r is equal to epsilon star, which means the material has failed within steady state itself. The material has not really gone into the tertiary creep regime. So, the material fails within steady state if lambda is equal to 1, and depending on the value of lambda you can have different amounts of tertiary creep strain contributing to the process. Now, Ashby and Dyson, they have observed that every damage macro mechanism has its own characteristic lambda value, and naturally depending on the characteristic lambda value you can have a characteristic shape of the creep curve. And in a separate elsewhere Faniraj et al. Have established a correlation between the ratio of time to Monkman-Grant ductility, which is TMGD, and time to rupture Tr, and the damage tolerance factor lambda. So, they came up with a relation which was basically TMGD, which is the time to Monkman-Grant ductility. So, if you look at TMGD, TMGD is the point corresponding to epsilon . So, the uniform ductility, the uniform creep ductility is epsilon star, and the time corresponding to epsilon star is TMGD. So, TMGD is equal to the time corresponding to epsilon star. So, it is basically the amount of time that the material requires to achieve a strain of uniform creep ductility of epsilon star. So, they took epsilon this TMGD and they took Tr, which is time to rupture, and then they proposed the following relation, and TMGD by Tr is dependent on lambda, which is the damage tolerance factor, and TMGD was suggested as a time. Faniraj et al. Basically suggested TMGD as the time for onset of true tertiary creep damage, and they hence said this can be considered as an important parameter in identifying the useful creep life of a material. Now, so for all practical purpose we would like our material to be deforming within the steady state creep regime only, because the moment we enter into tertiary creep regime creep strain rates are accelerated. So, the material is going to fail faster. So, how do you find out so what Faniraj et al. Are saying is if we stay within TMGD, then so the TMGD basically, because it is this time corresponding to uniform creep ductility or the amount of uniform creep ductility that can happen because of the steady state creep rate. So, TMGD corresponds to that. So, the TMGD can be taken as an onset of tertiary creep regime. So, if you look at the figure here, this is the point where the creep curve is taking off, and that is because of the contributions of tertiary creep damage, or that is where the tertiary processes have started, or the creep defect generation is now accelerated. So, they are saying that this TMGD can actually be looked at as a measure or the time taken for the onset of true tertiary creep damage, and hence it is an important parameter in identifying the useful creep life of a material. And it also describes the time, TMGD also describes the time till which minimum creep ductility is ensured, and hence Faniraj et al. Are proposing a design parameter. They are saying TMGD, the stress to cause TMGD in 10 to the power 5 hours can be used as a useful design criterion for creep of elevated temperature components. So, this is a different way of basically looking at things compared to what we discussed in terms of Larsen-Miller parameter and all that. So, this is coming from continuum damage mechanics. So, they have made a plot of, Faniraj et al. Have made a plot of TMGD by TR versus the damage tolerance factor, and when you have a very small damage tolerance factor such as 1, your TMGD is equal to TR, which means the failure will happen within steady state creep regime only, whereas if you have a large lambda, then your TMGD is basically coming down. So, if your TMGD is coming down, that means your onset of tertiary creep will be faster, but beyond a point for lambda greater than 4, TMGD by TR is essentially constant. So, there is no change in TMGD with respect to TR for lambda values greater than 4. So, this is basically introducing you to the continuum damage mechanics approach of modeling creep life and the different types of parameters that you can extract using the continuum damage mechanics approach. So, TMGD is something that we got, and we are also able to from the creep curve you can also determine the lambda value and then use it for modeling the creep behavior of materials. That brings me to the end to the portion on modeling creep life, the different models or approaches for predicting the useful creep life of a material.